The question is, the above diagram illustrates the basic design of a railgun, a very light rod with a mass of 2.60 grams and a length of 15.0 centimeter can move without friction on two parallel horizontal rails. Water break. Two parallel horizontal rails. The two rails are connected to a power supply that can provide a constant current of 5.00 amperes and are located in a perpendicularly oriented uniform 0.04 Tesla magnetic field. Okay, nice. So what happens here is there's some magnetic field here whose direction at the moment we don't know. And if the thing is like you see this thing right here, this black bar, it can slide on the rails like that, can go this way or that way. Now the rails end here, so if a force is applied on this really fast, what can happen is that it can shoot out like a gun. That's why they call it rail gun. Now why will there be a force? Because there will be some current and there will be some magnetic field. I don't know what there will be, what direction that magnetic field will be, but because of the magnetic field and the current in this, it will experience a force on the rightward direction or to the leftward direction, and it will move. Okay, we're gonna exactly see how that happens. So question 1 says, part 1 says, on the diagram above, show the direction of the conventional current in the rod. On the direction above, show the direction of the conventional current. Okay, so conventional current here, of course, because there's a positive in here and negative in here, you'll see that the current flows to this direction. Okay, that means it will come down here. That means will this come down here. So the thing is like, this bar is making electrical contact with the rail. So this is like a little circuit you've got here, and because the battery is like this, current flows out, comes back like that. Okay, so that is the answer for part A. That is the direction of the current. In what direction must the field be oriented in order to accelerate the rod to the right? Okay, interesting. So we use this again from your formula sheet, and this is I L cross B. Okay, I want to make sure this is correct. Yep, I L cross B. And the direction of I is same as the direction of L, right? So that's the convention. Like if you're wondering what will be the direction of the L when I will do the cross product, it is always in the direction of the current. Okay, so this is the direction of L. That is technically incorrect, but I just wanted to show you that. Now what happens is that the cross product's direction will be the direction of magnetic force, and that is where this rail will accelerate. So if we want this rail to accelerate in this direction, the force must be in that direction. And that is only possible if you've got magnetic field into the page in this region. Okay, try it yourself. Okay, curl your fingers of the right hand from the direction of the current, that is the direction of L, to the direction of the magnetic field, that is into the page. Your thumb will point to the right direction, to the right, and that will be the direction of the magnetic force, and only then this rod will accelerate to the right. So that will be the direction of the magnetic field. Now, what is the magnitude of the magnetic force on the rod? So this just means that I need to solve this problem, FB. Now, here, between L and B, it's 90 degrees, right? So sine of theta, when you do LB sine theta, will be just 1. And this will be ILB. So that means I here is 5 ampere. See this? 5 ampere. Length is 15 centimeters. If I convert that into meters, I get 15 times 10 to the minus 2, and B is 0.04. So let's do this. 5.00 times 0.04 times 15. It's 3 times 10 to the minus 2 newtons. 5, 15, 460, 65. No, I don't trust it. 5 times 15 times. Okay, this looks about right. What is the magnitude on this force is 0.003. Yeah, that's 3.3 times 10 to the minus 2. Now it says what is the magnitude of the magnetic force on the rod. That is exactly what we solved. And it says what is the acceleration of the rod. So as we said, there is a magnetic force to the right, and this can slide up and down or left or right on the rails. That means if there's a magnetic force, it's going to slide to the right, and what will happen next is as soon as it will get to the end of the rail, it will be launched like a bullet from the system. So that's interesting. So we need to find the acceleration. Always, like, force is given to us, and that is we just calculate. You just calculated it, and it was 10 to the minus 2 times 3, and that will be equal to mass times acceleration, and acceleration will be 3 times 10 to the minus 2. Mass of this rod is 2.60 grams, really light. That means it's gonna be 2.60 times 10 to the minus 3 kg, and this will be equal to 1.15 times 10 to the minus 1, or acceleration is 0.115 meter per second. 0. Okay, I don't trust it again. 3 divided by 2.6. Oh, fool. Come on. It's okay. Get 11.5 meter per second. That's a nice acceleration. 11.5 meters is about... How am I kidding? I don't know how much that is in feet. Sorry about that. But it's 11.5 meters per second. It's good. It's good acceleration. Now, how much time does it take for the rod to reach the end of the rails? Okay, so I'm going to make this... Alright, I'm going to use the same diagram. And it says how much time does it take for the rod to reach the end of the rails. So we know that there's a force in this direction, right? Because of the magnetic field, and there's current in there. Now, as we said, what will happen is this guy will start moving and it will accelerate. That's why we found the acceleration in part D. Now, it will reach the end of the rail and it will get launched off from these rails. Okay. Now, I just want to make sure. Now, you know what's coming. So we're going to be using again 2, 3, 1 concept here, where we know the acceleration, we know the distance, and we need to figure out what time it will take to get to that, to cover that distance. Okay, so... Okay, so that's part F. Oh my god. That's part F. So part E, which we have not solved yet, is what is the velocity of the rod as it leaves the rails. So to find out that, you just use this formula: V square equals to V naught square plus 2A delta X. Remember from your course of 231. Initially it is at rest, so this is 0. This means that V is equals to 2A delta X, and this means V is going to be 2 times acceleration is 11.5, and delta X, when converted into meters, 50 centimeters, is 50 times 10 to the minus 2, and this will give you velocity to be equal to about 3.40 meter per second. Okay, so that is part A. Part F says how much time does it take for the rod to reach the edge of the rails. How much time? Well, I know the final velocity, I know the initial velocity, I know the acceleration. So let's use this one. V equals, and the time is what I need. So V equals to V naught plus V acceleration times T. This is 0, there is no initial velocity. Finally, it's 3.40, and divided by the acceleration will give me the time, and time will be about 0.296 seconds. Wow, it's really fast. So it means if you set up this thing in a lab, what you'll find is this guy will accelerate with 11.4 meters per second square, and it will reach the end of this 50 centimeter rail in 0.296 seconds. That's really fast.